Moving forward, the next big kind of section of chapter 4 is going to be talking about buffers. So a buffer is any solution that resists changes to its pH. So you can imagine this is a solution that you have when you add acid or base to the solution, the pH does not change very much. So you can add acid, you can add base to the solution, and the pH doesn't change very much. This is really important. If you say have a chemical reaction, sometimes you are using acids and bases to drive chemical reactions. They're really common catalysts, especially acids. And so you want to have a certain pH that your reaction, say, has ideal kinetics at, really commonly. Or potentially you're trying to drive equilibrium, right? You're doing like Le Chatelier's principle. You want the solution to stay acidic because that's going to cause products to form or something like that. Biologically, it is extremely important. Living things have, are water-based solutions. A lot of aqueous chemistry going on in living things, and the pH needs to stay at a certain stable level in order generally for the living thing to exist, to prosper, for the chemical reactions to be happening in the right way, right? The acidity of a solution is really going to affect the kinetics potentially that's going on. It also really will affect the equilibrium that's going on. Generally you don't want, living things don't want pHs that are pretty extreme. They want to stay pretty locked in near neutral levels. So let's look at examples what this kind of really means to not have the pH. Let's say, what is the pH of 1.0 liters of pure water? Okay, 7. It's pure water. We know that that's our neutral solution, so we'd expect the pH is going to be 7. Great. So how does the pH change if we add 0.05 moles of HCl? Okay, so we're going to add some acid to it. HCl is a strong acid. It's 1 liter. I've added 0.05 moles, so I know that the concentration of HCl will be 0.05 molar. Because it's strong, all of that HCl produces hydronium, and the pH of this solution would be 1.3. So I added 1.8 grams of HCl, and the pH changed a lot. I went from 7 to 1.3. That is not a small change in the pH. That is not resistance to the change in pH. So water is not a buffer. If you add acid or base to water, the pH readily changes in either direction. We want something that if you add a small amount of acid to it, not much change in the pH occurs. So there is one way to make a buffer, and that is a solution with near equal, not exactly equal, but near equal concentrations of a weak acid and its conjugate base. If you remember, the conjugate base of a weak acid is itself a weak base. So what you need to do is create a solution where you have near equal concentrations of a weak acid and a weak base, and you want those to be a conjugate pair. So you want the weak acid and weak base in the solution. That is the only way to make a buffer. So one of the things about that is buffers are always solutions. Pure water, never a buffer. Buffers are always solutions with at least 2 components. So let's look at some examples and think, are these things buffers? So one thing is you'll note all of our potential solutions have 2 things in them. That's going to be standard as we move through and starting to look at buffers, that we need to have 2 things in there. It needs to be the weak acid and its conjugate base, or weak base conjugate acid kind of thing. So first, 0.1 molar HCl and 0.1 molar Cl minus. That's not a buffer because HCl is a strong acid. That is a conjugate pair, but we would need a weak acid, not a strong acid. 0.05 molar HF and 0.05 molar NH3. Well, we've fixed the problem. HF is a weak acid, but this is not a buffer because HF and NH3 are not conjugates. These are both weak acids. One's a weak acid and one's a weak base, but they're not conjugates, right? They are entirely different. Nitrogen and fluorine, we know conjugates are just different by the H. Well, what about 0.02 molar H3PO4? I got the PO4, and 0.02 molar PO4 3-. I got the PO4s here, but still not a buffer. These are not conjugates, right? The difference in a conjugate would be 1 hydrogen, not 3. We're going 3 to 0. That's not a conjugate pair. Okay, well, 0.01 molar HCN, that's a weak acid. and 0.00000001 molar CN minus. That is a weak base, which is its conjugate. So we've got conjugates now, but these are not near equal amounts. This is like a reasonable amount, say like 0.01 molar. This is barely any cyanide. So this would basically be what would happen if you had just like a solution of HCN. We know at equilibrium, yeah, you do make some of the conjugate, right? It's a weak acid, some of the conjugate base is there, but this isn't a buffer. These amounts would need to be like 0.01 and then a value close to 0.01. So finally, this is a buffer. So in order to make a buffer, you have the conjugate pair. So you can see we have our acid, it's acetic acid, and then we have the conjugate, the acetate, and then importantly, we can see 0.003, 0.003. They're not high, but importantly, they are very similar. These are near identical, meaning that this solution is a buffer. So let's get some experience with kind of charting out buffers, seeing what we can and can't do, can't use to make buffers. So for each species, determine if it could be used to make a buffer, and if so, what salt could you add to make it a buffer? I have HF, HBr, NH3, H2O, and PO4 3 minus. Let's see how that goes.
All right, so we want to know if each of these substances could be used to make a buffer. And so when we're looking to create a buffer, what we would need is a conjugate pair that's a weak acid and a weak base. And so we can start, and if we look at HF, okay, so HF, that definitely has a hydrogen, so it could be an acid. And basically, if we remember for weak acids, we can look them up on a table. So like HF, hydrofluoric acid is on our weak acid, one of our weak acid tables, but we also just know it's not a strong acid. And so if it's not a strong acid, then it's going to be a weak acid. So because this is a weak acid, then yes. You can make a buffer that's based around HF. And in order to do that, because that's a weak acid, you would need it to be paired with its conjugate base. So the solution will need to contain HF and its conjugate base, which would be fluoride, or F minus. So the solution would have to contain HF and F minus. There's the weak acid, there's its conjugate base. And if you had both of those things in solution, that would be a buffer. Now, the thing you will note when you're trying to actually prepare this buffer, you can actually dissolve HF, that's a compound. If you go into a chemical stockroom, if you go look online, try to buy some chemicals online or go to a store, you won't just find pure fluoride, right? Because it's an anion. So it would need to be in a salt where it's paired with a cation, right? So this is the idea of why we think and talk about salts. When we're trying to put especially weak bases or bases in general into solution, since they are oftentimes anions, they need to be paired with a cation. And we want it in this case to be a neutral cation because the base is going to, or the buffer, sorry, is going to be F minus and HF. That's all we want in kind of the, and in terms of like active acid and or base in solution. So we want a neutral cation. So we're going to need a salt with some sort of neutral cation. And so, you know, common examples would be something like NaF or KF, right? Neutral cations are group 1A and 2A. You could also do something like group 2, calcium fluoride. Any of those would work. Oftentimes, sodium and potassium are pretty cheap as far as cations go. So those are the most common ones and easiest to use, and they have the highest solubility. But calcium fluoride also works. Magnesium fluoride, any group 1A or 2A. You wouldn't want to use like iron fluoride or zinc fluoride, because remember, those are transition metals, those main group metals. Those have acid-base chemistry in solution. So group 1A or 2A, salt or a cation to make your salt. So then when it dissolves, those salts will dissolve and produce fluoride, free fluoride in solution. Okay, so HF, you can definitely make a buffer. You just need to have HF and then a salt that contains fluoride. So then what about HBr? Okay, well, it's definitely an acid. So could that work? Could we just figure out what its conjugate is? No. because it's a strong acid. So no, it can't be a strong acid. It has to be a weak acid that's paired with its weak base. And basically the idea is, if you remember, weak acids, their conjugates are weak bases, and you want that pair of them to both be weak. So what about NH3? NH3 is not an acid. We write it that way with H in the back, but it is a weak base. So in this case, we have NH3 is a weak base. So that means, yes, weak acids and weak bases you can always use to make a buffer, right? Because we used fluoride up here. So you have to have a weak base component in your buffer. In this case, it's NH3. So that's the compound we can add. Because it is a base, we need the conjugate acid, which in this case would be NH4+. But again, that's a cation. You cannot add pure cation to solution, so it needs to be a salt with a neutral anion. There are fewer choices for neutral anions. They have to be an anion that is the conjugate of a strong base. There's not too many choices, but you could have like NH4Cl would be a good choice because hydrochloric acid is strong. NH4I, hydroiodic acid is strong, or like we just saw, NH4Br. Nitrate is also a common one, ammonium nitrate. Nitric acid is strong, but these are the most common ones we see. Would be ammonium chloride, iodide, or bromide. But again, basically the anion, you need an anion in solution because you can't just put pure ion into solution. It has to be a counter ion. And so that's what you would have there. And when you were dealing with buffers, it's almost always a salt is almost always going to be involved. Got the red pen out, which means H2O is again a no. This is not an acid, not a base. So no, water cannot be the base of a buffer. It has to be a weak acid or a weak base, something that causes the pH of water to change has to be in there, not water itself. What about phosphate? That is a weak base. It's an anion whose conjugate is not a strong acid, so this is a weak base. So again, yes. So because it's a weak base, we need the conjugate acid, which is just going to be, again, 1 hydrogen. Even though phosphate can take 3, it's just HPO4, 2 minus. And so you'll note both of these are ions, and both of them are these combined are the active components of your buffer solution. You can't put either of them purely into solution. So they need to be in a salt, both need to be in salts with a neutral cation. So your buffer would be made by mixing Na3PO4 and say Na2HPO4. Where the phosphate, the PO4 3 minus, and HPO4 2 minus are being added in, and the sodiums are just there to be a cation. It could be potassium would be another common choice. You just need a neutral cation.
Participation 3.6, question 1. State whether or not each of the following is a buffer solution. If so, what are the active components of the buffer? A, 1.0 molar NH3 and 1.1 molar NH4Cl, and B, 0.52 molar HCl and 0.48 molar NaCl. This is the first question on participation 3.6 due Friday, March 6 at 11:59 p.m. Link to the assignment is right below the document where these videos are posted. Again, state whether or not each of the following is a buffer solution. If so, what are the active components of the buffer? A, 1.0 molar ammonia and 1.1 molar ammonium chloride. B, 0.52 molar hydrochloric acid and 0.48 molar sodium chloride.
So, how do buffers work? So if you make a buffer, you would have, say, equal amounts or near equal amounts of a weak acid, for example, acetic acid, and its conjugate base, for example, acetate. And so the whole idea is you have near equal amounts of these things, of this conjugate pair, and so they are there, and when you go to change the pH of this buffer solution, there's basically two ways. You can either add strong acid or add strong base. And the idea of in a buffer is you added this conjugate pair where you have base and acid in the solution. So there's always something to basically absorb or react with the strong things that you add. So say you added a strong acid. Functionally, strong acids create hydroniums, right? They react with water really quickly. But now this strong acid has a weak base to react with. Okay, it has a weak base to react with. You get water, which is neutral, and then you get a weak acid, which does not affect the solution as much. The strong acid here is going to affect the solution pH a lot, but the weak acid isn't. Say you add a strong base, there is now weak acid to react with. You make neutral water, and then you make weak base. So the whole mechanism of what buffers do is that you have this conjugate pair where you have both weak acid and weak base. There is something for the strong acid and or strong base that you would add to react with. So it won't necessarily react with water. It won't affect the pH. Instead, it'll react with the buffer components and create weak acid or weak base, which has a much lower effect on the pH because they're weak. So if you think about pure water, say I add 0.1 mole of strong acid to pure water. Because it's a strong acid, it fully reacts with H2O, and I would create 0.1 mole of hydronium, right? It reacts via stoichiometry, and that would lead to a large change in the acidity of the solution because water just reacts with the acid to lead to the production of hydroniums. In a buffer, when you add the strong acid, the buffer is a solution where there's something for it to react with, namely weak base. So you take your 0.1 moles of strong acid, it reacts with the weak base, which reacts to produce its conjugate, which is a weak acid. You now have 0.1 moles of weak acid, and additionally, it's actually just more weak acid to what you already have. So the fact that it's a weak acid and that it's just a little bit more lead to you have a really weak reaction with H2O, so you produce a lot less hydronium. It's much less than the 0.1 moles of strong acid that you originally put in, which leads to a much lower impact on the pH. This goes back to our original definition of strong versus weak. Strong acids really affect the pH. The whole point of a buffer is the strong acid is turned into a weak acid, which will not affect the pH very much. The properties of the solution won't change all that much when the strong acid is added in. And so buffers are extremely important. They're chemically they're relatively important, but biologically they are extremely important. Your blood has an extremely complicated buffer system in it. The pH of human blood wants to stay right at 7.4. That 7.4 really is kind of locked in that the chemistry that is supposed to happen in your blood is happening with optimal kinetics and no other chemistry is occurring. Your blood is a really important solution that you don't want to have, say, random chemical reactions just starting to go on it. So the body has a lot of mechanisms to control that related to things like your breathing with having CO2 go into your blood where it reacts, produces acid. There are phosphate buffers, there are proteins participating in that. There are multiple complicated buffer systems. And basically, you want to be locked right at 7.4. And if it shifts really at all, say, to 0.01 across on either side, you are going to start to feel sick. You're going to start to experience problems, acidosis and alkalosis. And if you really start to push it, it is not difficult to have death occur because basically like your blood stops functioning correctly. You're not transporting oxygen appropriately because, all these concentrations of hydronium and hydroxide that starts to show up in all the chemical reactions that are occurring in your blood and starts driving and affecting equilibrium mixtures. And so buffers are extremely important biologically, not just blood is a really common example and a very sensitive example. and a very robust buffer, but also inside cells, inside every living thing. There are buffers all over the place that are working to kind of maintain the balance and maintain the conditions for life to thrive.
Okay, first video, and we've already got a question for participation 3-6. Let's do Friday. This is the end of chapter 14. Buffers, kind of the first idea, kind of a bit, we'll kind of go through 3 kind of topics: buffers, titrations, and then structure acidity relation. So got to finish buffers, and then we'll do the other topics. Plenty more videos in the set. I will. Oh, this is the first one. We got the homework due Saturday and the post-lab due Sunday for acid dissociation constants. Make sure you're taking care of all the week 8 assignments before next week's exam. This stuff's going to be on the test, so you want to do these assignments, try to get some practice here. If you have any questions or anything, let me know. Otherwise, I'll see you in the next video.